Welcome to the fifth lecture of our course module Communication Engineering. So in the last lecture, we have already seen the amplitude modulation, its basic equations, like what is the time domain waveform, time domain equations, and what will be its spectrum, okay, its Fourier transform we have seen in frequency domain. And then we have seen its both time domain waveform as well as its frequency spectrum. Okay, we have already seen its bandwidth requirement in the last lecture, and we have already seen its power requirement. So today in this lecture, we are going to see how to extract the message signal. Okay, because once we do the modulation, okay, from the modulated wave, so this was the modulated wave SAMT AC cos 2 by FCT plus mu AC by 2 cos 2 pi FC plus FMT and mu AC by 2 cos 2 pi FC minus FMT. So this was our equation, right? So how to get the message signal? So you remember that our message signal was mt equals to am cos 2 pi fmt. That was the our required message signal. So that message signal we need to extract from the modulated wave. So we have to see that how to uh, go for this extraction process, and that particular process is called as the demodulation. So how to define the demodulation? It is the method, or it is a mathematical process or a process that will be implemented on a circuit that will be able to extract the message signal from the modulated wave. Okay, so that we have to see how to demodulate the wave. Okay, how to demodulate the wave. So see, one I'm just going to tell you one of the very simplest way of doing the demodulation process. Okay, it is very much mathematical. You will be able to understand and follow this mathematics. So the most prominently that we can use for demodulation process is one of the method which is called as a synchronous or coherent demodulation. Okay, you note down one thing here is that for conventional AM, okay, we have more simple receivers, okay, than this synchronous or coherent demodulation scheme. But because of the underlying mathematics, which is easy to understand, okay, I'm just starting the demodulation process with this particular method, like synchronous or coherent demodulation of AM signal. Okay, so there are certain other method by which we can also demodulate the AM signal. And there is one very simple method which is called as the envelope detection. Okay, so that process can also be done to demodulate the AM signal very easily. And that is also having a very simple circuitry design. Okay, as compared to this, because in this case, you just see, first you try to understand what is the concept. Okay, what is the concept and how this message signal can be extracted, how this AM signal is actually getting demodulated. So first we have to start with this block diagram. You see in this block diagram of our demodulator, which is nothing but our synchronous or coherent demodulator. Okay, I will tell you what is synchronous or coherent means. So you can see here in this block diagram, here it is, we have a circuitry, okay, whose function is to do the product of the two incoming waves. Okay, so generally it is known as product modulator also. You will see that in the books, you will find that it is written as the product modulator because it is performing the function of doing the product of two signals. Okay, so first of all, what we have to do is, first one of the signal that we have to apply is our modulated wave. Okay, so we already have our modulated wave as SAMT. Okay, so this wave is going to be applied into this particular product modulator, and then another signal will be our same carrier wave. Okay, the carrier wave that we have used for modulation purpose. Okay, if you remember, the basic equation of our standard equation for our conventional AM was If you remember, it was AC 1 plus mu cos 2 pi FMT into cos 2 pi FCT. So this was our basic equation in which we had used the our carrier as equals to AC cos 2 pi FCT. Okay. So in case of synchronous or coherent demodulation scheme, we have to use the same carrier at the receiver end also. Okay, at the receiver end. So basically demodulation has to be performed at the receiver end. Okay, we have already done the modulation at the transmitter end, and after the performing the modulation, we could fed that particular signal to the antenna, and antenna will radiate that signal, and after traveling through the channel, okay, it will be received by the receiver antenna, and in the receiver antenna this signal has to be fed to this particular demodulator circuit. Okay, so what we are saying that this synchronous or coherent demodulation scheme of AM signal, the synchronous or coherent means we have to again use the same carrier signal that we have used for our modulation purpose. Okay, so it has to have the same carrier frequency as well as phase. Okay, as the wave we have at our uh, transmitting end. Okay, for the modulation purpose. So you remember that the synchronous or coherent really actually it is related to the frequency part and the phase part of the carrier. Okay, so if the frequency part and the phase part of the carrier that we are using at the receiver end, okay, is same as the carrier that we have used at the transmitter end, then this scheme is called as synchronous or coherent demodulation of the EM signal. Okay, so you just see the very simple mathematics that we have is first of all we need to multiply the same carrier. You remember that its amplitude doesn't matter. Okay, you could have chosen like AC dash or AC. Okay, it doesn't matter. Okay, whatever may be the amplitude, it doesn't matter. Okay, things that matter is this frequency. Okay, this frequency part and the phase part of this particular carrier signal that we are going to multiply at this demodulator. So let us suppose we are multiplying the cos 2 pi fct. So if we multiply cos 2 pi fct, okay, then this product will be represented as Vt. Okay, so I have represented here it as Vt, where this first part, okay, this first part is our SAMT. Okay, it is SAMT. Fine. So this first part is representing your modulated AM modulated wave. Okay, and this next part, this part is representing you the carrier, this part. Okay, so we are multiplying this two, and after multiplying this two, we can easily show that after this multiplication it will become cos square 2 pi fct, and if you further expand it by the formula, you will get 1 plus cos 4 pi fct by 2. Okay, now again we can expand it further. Okay, it is a very simple expansion, and we have to use this formula again, cos a cos b formula, and after substituting this formula and expanding it, it is very easy to show this equation. Okay, we are going to get like AC 1 by 2. Okay, so it is AC by 2. Then further we can write this equation like AC by 2, here it is cos 4 pi fct. Okay, AC by 2 cos 4 pi fct. Okay, similarly you can write all other components of this equations. Okay, like it is mu, here it is, so it is mu by 2 cos 2 pi fmt. Okay, it is mu AC by 2, so mu AC by 2 cos 2 pi fmt, and all rest of the part we can write. And after that, we will be going to get this particular product term cos 2 pi fmt and cos 4 pi fct. Okay. And on to that particular product term, we have to use this formula, okay, of cos A, cos B formula. So ultimately, we are going to get this equation. You can see this equation. Okay, Vt equals to AC by 2, AC by 2 cos 4 pi fct plus mu AC by 2 cos 2 pi fmt and mu AC by 4 cos 2 pi 2 fc plus fmt and mu AC by 4 cos 2 pi 2 fc minus fmt. So this is one of the very important equation, okay, very important equation after multiplying the same carrier again to this modulated way, okay. So this is what we are going to get Vt, okay. So this equation we are going to get. Now from the equation itself, what we can see is we can easily identify the frequency components which are available in this particular equations. For example, you can see that the first term is AC by 2. So this AC by 2 represents you the DC component. It is a DC value, okay. For example, if we write any equation, for example, 1 plus cos 2 pi fmt, okay. So in that case, 1 represents the DC part, okay. So similarly, here it is AC by 2, it represents the DC component, okay. Now we have one AC component, okay, and this AC component is actually having its carrier frequency at 2fc, because here you can see that it is cos 4 pi fct. So this can further be written as cos 2 pi 2 fct, okay. So this carrier is at 2 fc frequency, okay, whatever be the carrier frequency that we choose, so it will become at 2 fc, okay. Similarly, here you can see that there is another cosine term, okay, at fm frequency, okay. So basically if you see here, it is at fm frequency, here it is at 2 fc frequency, okay. So one of the delta function, okay, uh, because it is a cosine function and we know that its spectrum will be a delta function, okay. So that delta will occur at 2 fc, and here it will occur at fm, okay, fm and minus fm. Here it is at plus 2 fc and minus 2 fc. Here you can see we are having another frequency component, okay, which is at 2 fc plus fm, and one more at 2 fc minus fm, okay. So from this equation itself, we can see that there are several frequency components which are going to available in the spectrum of Vt, okay. So there are several frequency components. So now after having this several frequency component, what we are intended to get, we are trying to get the message part only. So basically what is our purpose? Our purpose is to extract the message part. Here you can see that this is our message part, okay, because this is cos 2 pi fmt part is available at this point. So our main task is to filter out all rest of the signals. All rest of the signals we need to filter out, okay, because these parts are not required, okay, these parts are not required. Only we want to have this particular component. So how to do that? How to remove these terms? So the answer is we have to use a certain low pass filter. Why we are going to choose a low pass filter? Because we know that all rest of the frequency component, if you observe, they are at 2fc, 2fc plus fm and 2fc minus fm, okay. So we have already established that our carrier frequency fc is much greater than the fm, okay. We know that, okay. So our carrier frequency itself is a very high value. It means that it is a higher frequency component. You can see that this is 2fc, it is a higher frequency component. Again it is 2fc plus fm, it is again a higher frequency component. And again it is 2fc minus fm, it is again a very high frequency component. So only this is one of the component which is having low frequency part, okay, because it is 2 pi fm, so it is fm, okay. So it is having a low frequency part. Similarly, here we have the DC value. So generally DC value doesn't means give you any problem, because this can be easily rejected by having a DC blocking capacitors, okay. In any circuit we can have a DC blocking capacitors, and it will be easily removed. DC component can easily remove. So that's why, because we want to filter out the high frequency components, we have to apply one low pass filter, okay. So we have to apply one low pass filter. So basically when we pass this signal Vt through a low pass filter of a certain cutoff frequency, so that only this part is means will be allowed and all other parts will be rejected, then the output of this low pass filter, okay, output of this low pass filter will be something like mu AC by 2 cos 2 pi FMT. Okay, mu AC by 2 cos 2 pi FMT. So here we can further write this equation as mu we have already defined. So our mu will be equals to how much? It is Ka into Am. Okay. So our mu is modulation index is defined as Ka into Am. So here you can write KAAC by 2, or here Am we have written here. So Am cos 2 pi FMT. So basically here this part is nothing but our message. Here you can see it is Am cos 2 pi FMT. Okay. So what we can say is there are some additional factor which is coming into the output, which is KAAC by 2. Okay. So you remember that this output, V output of the low pass filter is proportional to our message signal. Okay. This is what we wanted. Okay. We want that this output of the low pass filter should be proportional to our message signal. You remember that this additional factor never imposes any problem in communication system, because it is just going to either attenuate the signal if this factor is less than 1, or if it is greater than 1, then obviously it is going to amplify the signal a little bit. Okay, it means that its strength is going to change. Okay, there will be no any other effect. Okay, so we can have any simple amplifier circuit whose gain can be like, if it is here it is Ka upon AC by 2, we can make an amplifier circuit whose gain will be equals to let us suppose 2 upon Ka upon AC. Okay, and that time this factor will be cancelled out. It is very easily we can cancel out this particular factor, so it is not a very big task. Okay, so you please do not bother about this factor which is coming in front of this particular message signal, because this can be handled easily by having a amplifier of certain gain. Okay, so let us suppose if I say that this gain is G, then I can design a amplifier of gain 1 upon G, and then this G and G will be cancelled out, and we are going to get the exact message signal empty. Okay, you remember that this frequency part is very important. Okay, that should not be disturbed. So this way we are going to get the our message signal. Okay, we can demodulate the AM wave and we can get the message signal. Now we can again see the same thing from the spectrum point of view. Okay, we can plot the frequency spectrum of this particular equation Vt, and then we can take ideally a low pass filter. Okay, its frequency response of the low pass filter, and then we can see how this filter is going to reject all other higher frequency component. So here you can see that we are having 1, 2, 3, and 4. Total 4 cosine functions. Okay. So as we already seen that one cosine function can give you two impulse functions. Okay. One at positive frequency, another at negative frequency. Okay. So all together we are going to get total 8 impulse functions, 4 positive side and 4 negative side. Okay. And here we have a DC component AC by 2. So for a DC component, okay, we have the its Fourier transform equals to delta f. It means that we are going to get another impulse at delta f, means f equals to 0, because it is a DC component. Fine. So one delta function will come at f equals to 0. Okay, whose magnitude will be equals to 1 if we are plotting the spectrum in f domain, frequency domain. Okay, if it is in the omega, if axis will be choosing on omega, then it will be 2 pi. Okay, 2 pi delta omega. So that we remember. So now you just see what will be the spectrum of this particular equation that will look like. So the spectrum will be look like something this. Okay, you just see this one. So basically here you can see I told you that we have one of the frequency component at FM. Okay, FM whose magnitude is mu AC by 4. Okay, you can just go back to the previous slide. Here you can see that we have one frequency component, okay, here cos 2 pi fmt, its magnitude is mu AC by 2. So when we calculate the Fourier transform, it will become mu AC by 4. So here we have this component, okay, whose magnitude is mu AC by 4 at Fm and minus Fm. Similarly, one frequency component we have already seen at 2Fc, okay, it is at 2Fc, and again it will be at minus 2Fc. And then we have the frequency component at 2Fc plus Fm, one more frequency component at 2Fc minus Fm. Okay, and accordingly I have written its amplitude, okay, based on that particular equation. Okay, and I told you that another delta function should come at delta f, okay, means f equals to 0. So this is our f equals to 0. So here we are going to get another delta function because it is a DC part. Okay, so DC component. So at this point another delta function is coming, whose magnitude will be AC by 2. Here you remember that we are plotting this spectrum in this x-axis in frequency f. Okay, it is not in radians, omega. So whenever if you are plotting the same thing onto the radian, you remember that a little modification in all these magnitudes will happen. That you have to take care. Okay, so now if this is our spectrum of our signal Vt, okay, which is the product of our modulated wave and multiplied with the same carrier. So this was the this was the spectrum. Okay, so now if we are choosing a certain low pass filter, okay, ideal low pass filter, so the ideal low pass filter will have its frequency response like this. Okay, it will have this type of frequency response, ideal low pass filter. It will have a certain cut of frequency, okay, 3 dB cut of frequency you can say, or because it is ideal low pass filter, it is having a brick wall approximation. Okay, so generally it is an ideal here whatever I have plotted the frequency response is for an ideal low pass filter. Practically we are not going to get this type of response. You will be getting like this. Okay, there will be a certain roll off factor. Okay, it will be decreasing slowly. Okay, it will be decreasing slowly. It will be depending on what is the order of the filter. Okay, so let us suppose if we are choosing an ideal low pass filter. Okay, here we can see that the pass band of this filter is this. Okay, within this 0 to certain frequency, it is allowing it to pass through. Okay, any frequency component up to this point will be allowed, okay, by the filter. And let us suppose that if its magnitude is 1, then it will be passing this signal those signals whose frequency is less than this particular cutoff frequency. So after that you can see that it is having its stop band. So here we have the pass band of the low pass filter, and after that we are having the stop band. So after a certain frequency, it is not going to pass the signal. It will be rejecting all the components. So simply, if we have this type of low pass filter, okay, followed by this product, okay, Vt, then obviously only this component is going to be passed, and all other high frequency component will be rejected because it is doesn't falls under the pass band of the low pass filter. Okay, so it will be rejected. Okay, it will be rejected. And we know that after passing through the low pass filter, this component will also be available. Okay, I have not shown here because what I am saying is this component can be rejected by having a simply DC blocking capacitors. So after passing through the DC blocking capacitor and low pass filter, we are going to get this type of spectrum. Okay, and this spectrum is nothing but our spectrum of our massive signal. Only things which is changed is its amplitude. Okay, so please do not bother about its amplitude. As I already said, this can be taken care of by having a certain amplifiers of certain gain. So this way we are able to get the massive signal back from our modulated wave. So I hope this discussion must be clear. Now we have to look at one more point. Let us suppose if this carrier component that we have taken, because we have talked about that if we are doing the synchronous or coherent modulation. Okay, and in that synchronous or coherent modulation, I said that this carrier should be having same frequency and phase uh, with respect to the carrier that we have used for the modulation purpose. Okay. Now let us suppose that if the carrier that we are using for the demodulation purpose, okay, is not having the same phase, okay, as we have used for our modulation. Okay, so at the modulation end we have used cos 2 pi fct, and now let us suppose at the demodulation end, if instead of having cos 2 pi fct we are having a certain phase shift, okay, of phi. Okay, if we introduced any phase shift in the carrier, what is the effect that we have to look at? Okay, so just try to give this offset of in the phase of the carrier, and now it is no more synchronous. Okay, it is no more, so it is not synchronized in phase. Okay, this particular carrier that we are using at the receiver and for demodulation purpose is no more in phase synchronized. So when it is not phase synchronized, then we can do this simple mathematical analysis again. So if you just expand these signals, okay, and if you do the multiplications, okay, we are going to get these equations. These equations are very easy to identify. Please do this mathematics. Okay, so finally after doing this expansion, okay, and by using the formula, okay, we are going to get this particular equation. Okay, here you can see we are going to get the Vt equals to this particular equation. Vt equals to AC by 2 cos 4 pi fct plus phi plus cos phi plus mu AC by 4 cos 2 pi 2 fc plus fm plus phi, and again here it is 2 fc minus fm again plus phi. Here it is 2 pi fmt minus phi and 2 pi fmt plus phi. Okay, so here we can see that we are going to get a certain phase part. Okay, certain phase part. So as I said that again it will be passed through the low pass filter. Okay, basically what happens, this high frequency component will be rejected again, okay, by the low pass filter irrespective of its phase part. Okay, it won't be depending on the phase part, but basically it will be depending on the frequency part. So this all high frequency components will be rejected again by the low pass filter, but the output of that filter will again be this particular massive signal, but now it will be a little bit modified. So here you can see that our masses component is available in this part. Okay, mu AC by 4 cos 2 pi fmt minus phi and mu AC by 4 cos 2 pi fmt plus phi. Okay, so this is our message part. So this part will be actually passed by our low pass filter, and all other part will be rejected by the filter because they are high frequency component. So after passing through the low pass filter, this will be the output. Okay, so this output is mu AC by 4 cos 2 pi fmt minus phi plus mu AC by 4 cos 2 pi fmt plus phi. Okay, so now what we can do is we can further rewrite this equation, okay, by just following the formula. Okay, cos a plus b plus cos a minus b. Okay, by following that particular formula we can write this equation as mu AC by 4 2 cos 2 pi fmt multiplied with cos phi. Okay, so further it can be rewritten as V output T KAAC by 2 AM cos 2 pi FMT cos phi. Okay, so a little modification I have just done. So here again you can see that this is our message part. Okay, AM cos 2 pi FMT, this is our message part, and this is again a proportionality factor, you can say, or additional factor which is going to be multiplied, and another factor which is going to multiply it is cos phi. Okay, so if you compare from the last equation of our output equation was V output was directly proportional to empty in the previous case, but now when we have introduced the there is a phase shift in the carrier signal, the output will become proportional to empty cos phi. Okay, it is empty cos phi. So what does it mean? Whenever this phi is equals to 90 degree, there is a 90-degree phase shift between the carrier that we have used at the modulation and at the demodulation, and that time cos 90 will become 0 and the output of this demodulator will become 0. Fine. So what does it mean? Whenever there is a 90-degree phase shift between the carrier at the demodulator and at the modulator end, okay, then there will be a loss of message. Okay, message cannot be recovered. Okay, message cannot be recovered. Okay, you remember that message cannot be cannot be recovered because of the 90-degree phase shift between the carriers, okay, that we have used at the modulation and demodulation end. So this phenomena in which the message signal at the demodulator is actually lost is called as quadrature null effect. Okay, quadrature null effect. So why it is quadrature null effect? Because here the carrier is in quadrature phase with respect to the carrier at the modulator end. Okay, so it is called as the quadrature phase. When it is 5 equals to 90 degree, then it is called as quadrature phase. Okay, there is a 90-degree phase difference between the carriers, okay, that we have used for modulation and demodulation purposes, and that time our output will become null or 0, and that's why we are calling it as a quadrature null effect. Okay, whenever there is a big 90-degree phase shift. Okay, so that we have to remember that in the synchronous detection, this carrier must be very much synchronized in phase as well as in the frequency. Otherwise there will be a certain errors that we have to tolerate. Okay, and whenever phi equals to 90 degree, the message will be completely lost and we cannot recover the message signal. So remember that whenever cos phi or phi is equals to 90 degree, that time only message will be lost. Even if phi is equals to, let us say, 30 degree or 45 degree, this value is going to be less than unity, and that time a little bit attenuation of the message signal will take place, but still it is possible to recover back the message signal by having a certain amplifiers of certain gains. Okay, so the only problem when it is phi equals to 90 degree, at that time the message will be completely lost, and we can call it as the quadrature null effect. Okay, so I hope that this discussion must be clear. You please try to work out this equation. Okay, this equation is very simple to do. You will be able to get this equation. So try to work out this. I think you will be able to perform this and you will be able to get these equations. Okay, and you just try to do this simple analysis. So you remember that amplitude modulation means amplitude modulation conventional AM. Whenever we are doing the demodulation using synchronous or coherent detection, then there is a chance of quadrature null effect. Okay, there is a chance of quadrature null effect if there is no phase synchronization between the carriers, that you remember. So I will be discussing the multi-tone modulation in the coming lectures. So if you have any doubt, please drop your query into the comment box. So thank you for watching today. I will be discussing the next topic in the coming lectures. So please stay connected with my YouTube channel. Thank you for watching.